Okay, the second part of week one, we're going to talk about the atmosphere, just looking at the atmosphere as a whole. So rather than just focusing on weather at the Earth, weather is created by looking at the atmosphere in its totality. The atmosphere is relatively thin. You think about it, if you're driving across Ohio, how long does it take, or how many miles is it? Yet if you look at the atmosphere, it's basically only about 20 miles high. Not even as far as driving from Mount Vernon to Columbus. So really, it's a very thin layer of air that helps us in every way we live. So, and there's also the Earth system is kind of like the atmosphere. We're going to be talking a lot about that. The hydrosphere, which is more liquids like the oceans. Geosphere, land masses. Think of volcanoes, your continents. Biosphere, think of your plants growing around your yard. Trees, that's the biosphere. All three or four make up the Earth. But we're going to focus, and all contribute to the atmosphere. But we're going to look at the atmosphere as a whole in this whole course. So rather than worry about its evolution and all of that they talk about in this book right now, we're going to deal with what it is right now. What does it look like if you looked at the atmosphere right now? So the atmosphere right now consists basically of 78% nitrogen. It's a lot of nitrogen. 20%, almost 21% oxygen. So really, the rest of the gases in the atmosphere are relatively small amounts. About 99% of the gases in the atmosphere are oxygen and nitrogen. You see this percentage here, 20%? And you see this nitrogen that says 78%? If you were to go up on top of a mountain, say Mount Everest, the oxygen percentage would still be 20%, and so would nitrogen. But because you're on top of the mountain and there's less atmosphere there, atmosphere gets less and less the higher up you go, that 20% isn't going to give you a lot of oxygen to breathe. So that's why as you go up higher and higher, you feel less and less oxygen getting into your lungs. Because even though the percentage of oxygen is the same, the amount is different. So moving down through here, you can see all the different gases, just a listing of them. Think about carbon dioxide. It's really not a big amount of gas, but it has a lot of influence on our weather. Water vapor can sometimes come in there and make up to 4% of the atmosphere on a really humid day, and I mean really humid day. But mostly it's, it varies greatly, and it's really many times less than 1%. There are aerosols in the atmosphere. You ever seen dust getting blown from a field? Maybe even factories and stuff putting particulates up into the atmosphere. They impact how that weather is going to be at your house. We're going to talk about why as we go through this book. If there's too much of an aerosol, and I lived in Charleston, West Virginia for about 12 years almost. And at that time, back in the 70s, there was a lot of chemical plants there. And they did put a lot of aerosols into the atmosphere. And you could really tell it in certain areas of driving through the valleys and all. So air pollution has gotten a lot better over the years. And we've got working our way to improving it all the time. And some of these pollutants are harmful. Sometimes there's accidents that happen, and they can cause problems. There are various standards the EPA has developed for air pollution to try to protect your health. We talk about the scientific method. Basically, scientific method is you ask questions. If you looked outside and wanted to ask a question, a simple question, and then you form some kind of hypothesis about an answer. Then you do observations to see if that makes any sense with what you're seeing. You might even test a hypothesis to see if it, correlates to your observations in your analysis you get. And as you do this, it's basically the scientific method. You keep coming back. Do you need to change the hypothesis? If it's no good, redo it again. We're seeing a tremendous amount of this method being used with COVID-19 right now. You'll see the papers that come out, and all of them have used this basic method. Some of them may have skipped steps somewhere in here, and that's why they have to repeat that method again and again. But they're all asking questions about that disease, trying to form hypotheses, trying to observe, gather data, trying to do analysis on that data, and then see if it makes sense. And then report the results back into other people to look at, to verify. So this is a basic scientific method. You're really seeing it played out literally in the news media as we go through it right now. How do we look at the atmosphere? We look at it from different atmospheric models. There are conceptual models where we make a statement about the atmosphere. There are graphical models where we draw pictures. You've seen the last video I did. It just talked about the surface weather map. It's a nice graphical model. We have some physical models where we'll put maybe a chamber together and try to generate a small tornado within a chamber. Just trying to understand what's happening with the weather. And then here's an example of that. Then there are mathematical models. We're not going to cover a lot of math in this course, so don't get worried. But math is a way of representing what the atmosphere is doing and what it's going to do in the future. Unfortunately, we can't solve the equations that govern the atmosphere. There's no math out there that has ever solved that equations, but we can approximate, and we can delve into more and more sophisticated approximations that try to solve it. And especially when we get down to very high, say I want to just look at the weather at Mount Vernon and just look literally maybe in the state of Ohio, that's very high resolution. We're very curious on what is going on literally at your house in the state somewhere. And that's how we look at it with these mathematical models. So there's also all kinds of surface observations, and right now most of the surface observations are done by ASOS. ASOS is put at a lot of airports. Almost all airports have some form of ASOS. And the reason they have that is you're flying an aircraft. You cannot land if you don't know what the conditions are where you're landing, or you can't take off if you don't know what the conditions are where you're taking off. So having these ASOS equipment there, they need to know that weather. And that is, for example, here's the winds, this little anemometer up here. Notice how much higher it is. Wind speeds, the ones you hear on the radio, are literally wind speeds that are at that height, which is 10 meters up or about 33 feet in the air. Here's your temperature over here in this area. And temperature is taken about 3 feet up above the ground. It's not at the ground. It's 3 feet up, and there can be a big difference in temperature. So there's all kinds of instruments that observe the weather here, and they're all over the country, these instruments. There's lots and lots of them. Think about all the airports you see in Ohio or in other areas of the country. You have one of these sensors almost at every single airport. Here's a cooperative network. Here's a shelter, rain gauge. What these do is they take daily observations, but they may only report these observations once a month. The idea is to get climate. So they have one of these in every county in the U.S., trying to get an idea of the climate long term in the United States. We talked about the atmosphere being three-dimensional. We send up balloons, literally send them up every 12 hours. Sometimes with the weather's really bad, we might send them up every 6 hours. All they are is you put a big balloon here, a big ball in the sky. Oh yeah, look how small that balloon is right there. Well, when it's done, it might cover a whole area big as this. Huge size. Why is that? Because as it's going up in the atmosphere, there's less atmosphere. The amount of the atmosphere gets less and less. So the balloon has to expand until eventually it breaks. It breaks about 100,000 feet up. And there's a parachute on the instruments, and sometimes they fall back down. They could even fall back into your house. So there are the closest one in Ohio. There's one observation point in Ohio. It's near Cincinnati. And there's one there. And there's another one. Pittsburgh has one. Next closest one probably would be near Chicago. So there's not a lot of these observations around, but we can get a feel for what the atmosphere is doing by looking at them. And there's your radio sonde that goes up with them. There's something called a drop sonde that comes out of an aircraft into hurricanes and stuff that'll track the pressure, the winds. Radar. Right now there's radars all over the country, and you can actually see up here in Ohio right now there's some rain. If I were to click on just look at the reflectivity right here, you see some showers. Get a little bit closer detail around Columbus and coming through that area. So this is just a way of looking at the rainfall, what is going on now. But let's compare this. See, there's a shower here in Zanesville, shower here in Columbus. If I were to look at the GOES imagery, see the clouds? You can't tell a whole lot where those showers are. But combining that with the radar, now I can pick out the intensity of the rain, maybe relate it. I looked at infrared, maybe I can relate it to how bright the clouds are. So I get a whole lot of information by that. One of the other things satellites do for you is you can measure winds. And let's get off of this one a second. These winds are at different elevations. The red ones are relatively high up in the sky. The yellow ones are partway up, and the white ones are about near the ground. So you can actually pick on clouds, try to see where they go. And with that, you can see all kinds of different wind directions that are circulating around here. You see out in the waters right now, there's a lot of lower winds that are coming out of the east and southeast. High winds are coming out of the southwest. So you really get to see the atmosphere has winds in all kinds of different directions here. So as we move down through here a little bit more on the observation side of it, you develop temperature profiles. The atmosphere has this troposphere. That is where we live. That's where weather occurs. Then there's a layer called the stratosphere. Notice the temperatures begin to warm in the stratosphere. So that's something we kind of use to differentiate it. Tropopauses, temperatures tend to cool all the way to it. And then they begin to warm. When they begin to warm is where we begin to identify the stratosphere. So there's a tropopause, stratosphere, stratopause, then a mesosphere. Again, temperatures begin to cool. And the thermosphere where they begin to warm back up again. So we can plot those and get all kinds of information about the profiles, but we're really weather looking at the troposphere. The ionosphere, obviously that impacts auroras, and depending on the amount of solar wind, it depends on how much auroras there may be, even where they may be found in the world. Here's a pretty picture of one. And here's actually, there's a space weather center in Boulder, Colorado that actually makes forecasts of where you might expect to see the northern lights. The final thing I just wanted to look at quickly is this week's weather. And we'll talk about this as we move on to other things, other weeks. But if you were to make a forecast, you'd want to know what's going on in the weather. Well, this is valid for 8 a.m. Sunday. We saw that cold front that was up there. Well, it kind of weakens, but there's still a front right along the East Coast. And with time, that front's still there. Never seems to move away, even a little bit of low pressure there. So if you're living or planning on going to the Southeast for a vacation or something this week, not going to be a good week. It's live in Ohio, it looks like the sun might come back out mostly by tomorrow and be all right then. A little bit cooler than normal. So that's what we're going to talk about, is how to forecast this weather. This isn't weather. This is weather forecast. And that's what you're interested in. You want to know what the weather's going to do, not always what the weather is. But in order to know what the weather's going to do, we got to know what the weather is first. So let me know if you have any questions, and we'll look forward to reading your discussions this week.